This is lecture 16 of Computer Science 147, Computer Architecture Study. In this lecture, we'll talk about uh, ILPs and hardware threading. Two concept. Actually, ILP is more like a combination of different concept on how can we make the performance better uh, with respect to the pipelining concept that we had in earlier lectures. So they're called ILP. Full form is instruction level parallelism. The idea here is that as in the pipeline, we want to execute two or more independent instruction in parallel to boost up performance of a processing system. So one such system from single no parallelism to kind of a parallelism we did on the pipeline, where we were executing like three different instruction in the pipeline, not truly in a pure parallel sense, but somewhat parallel, right? Because they're still not completely overlapping with each other. So, but anyway, that boosted up our performance on theoretical bound of number of pipeline stages, right? So, if you compare the performance of a pipeline system with a non-pipeline system, which has a 5 stages of execution of an instruction, then our performance gain is upper bound is 5x, right? 5 times it faster the system would become. Now the super pipeline concept, okay, so this was our pipeline. Okay, so from the previous slide, it was like no pipeline on the upper part of this diagram. The lower part was pipeline. Now, next concept, from pipeline to a super pipeline, where these pipelines are made kind of, these instructions are executed with a half clock cycle. So basically, not only the positive edge at the positive edge these pipelines are being active, but pipelines are active in the negative clock edge as well. So we're kind of making double performance improvement with super pipelining strategy. Of course, you can imagine our circuitry will go up more complex in this case to really fine-tune control the signals, and since they are not ideal, they will have dependency, they will have hazard, all the different hazard we talked about in the pipeline discussion, all of them are there and they will become more complex. But anyway, people does it to gain further performance improvement. Upper bound in this case is 10x performance improvement. So that's what is given here in this slide. For a balanced n-stage super pipeline structure, the maximum speed up obtained is 2n. So normal pipeline that we discussed in earlier lectures, that would have 5x gain on the performance side, but this one super pipeline will have 2x performance. Here in this case, like we're representing it as a 2n performance with respect to the non-pipelined system, where n is the number of cycle it takes to complete one instruction. For our Da Vinci processor, that CS147 DV instruction set implementation, that has a 5 cycle. Like MIPS processor has a 5 cycle of completion. So if you think of a MIPS pipeline, it would have a 5x performance improvement in just normal pipeline, and if you implement a super pipeline for the MIPS processor, you will get 10x performance improvement. All right, so that's what it meant by 2n, where n is the number of cycle to be completion, number of cycle of completion per instruction. Now this is what it explains in this slide in words. For a balanced n-stage super pipeline, the CPI, clocks per instruction, is improved by 2n times, where n is the number of cycles to complete one instruction. Since each stage of super pipeline is completed with double efficiency compared to a normal pipeline. So with respect to the normal pipeline and super pipeline, your comparison or performance improvement is 2x. Okay, and with comparison with the baseline system, which is non-pipeline system, you have 10x in terms of if you are making a super pipeline of MIPS processor. Now from the super pipeline to the superscalar, now we are not satisfied with half clock cycle alignment. We want to really make two instructions execute in parallel. So they call it superscalar system. And of course, you can imagine from there we can actually do n, right? N instruction in parallel. Just put some additional hardware, make it n instruction in parallel. So that's your superscalar. Now, scalar versus superscalar, architecture wise, what we can think of from theory perspective, right? So our system, pipeline system is what? Like we have register file, we have memory where the data exchange takes place, right? Read and write between these two storage components. And there is a pipeline data path which crunch information from the register file and commit the result into the register file. That's the scalar system with a pipeline. Now superscalar would be like you deploy multiple pipeline. So in this previous slide, the diagram we have shown there is basically using two parallel pipelines. So that's why it become two instruction truly going in parallel. Now for the superscalar, you are not bound to with the 2 or 4. You can just, depending on your need and how much you can push into the silicon, you can have multiple level of pipelines there, right? Multiple number of pipelines there. You can have 10 pipelines if you want. If it needs, if it suits your business need, you can make such a processor. You can implement on the silicon, and that's fine. Now, superscalar performance improvement is basically with respect to the non-pipeline is your M multiplied by N, whereas M is your number of pipeline you are attaching in the system, okay, deploying in the system. And N is cycle per instruction per pipeline, okay, cycle per instruction per pipeline. Let's take in the MIPS example. Your CPI there is 5 because it's a 5-stage operation, always 5-stage execution always for an instruction. So it's a 5-staged pipeline, and you are deploying, let's say, 10 of them. So your performance improvement with respect to a non-pipeline system with the superscalar would be 5 multiplied by 10, which is like 50x gain. So for a superscalar structure, which M number of n stage balanced pipe CPI improved by m minus n, that m multiplied by n, that means if m is 2, it matches performance improvement with a super pipeline. Remember, in the super pipeline, we did what? We are executing the pipeline stages at the each half clock cycle time, okay, half clock cycle time, where it basically improved by 2n, right, with respect to the baseline non-pipeline system. Now, if you deploy a superscalar system which has a 2 pipeline, it matches exactly that performance improvement, 2x, right? So this is all about, you need to know in the instruction level parallelism or ILP concepts. These are all abstract concept for sure. But you need to start imagining things, right? Right now, as I said earlier, we won't be discussing more details how things are done and stuff. They're super complex, basically. But conceptually, at least we need to know as a computer science people that, okay, these systems are there and this is their performance benefit. And if if in my work area, like in your work area, like when you join a company or work for a company and you are basically in a position to decision making to, let's say, uh, build certain system or buy certain system, then you need to analyze this your business requirement and go for right kind of machine architecture for your problem space. So these are few examples out there where by through which you can actually really improvement performance at the very ground level, at the hardware level.